Hello and welcome back. We're going to talk about the calculus of parametrics today, more specifically how to take their derivatives. Now before we begin to the derivative of a parametric, we have to review how to take a derivative itself. Now we are going to use that Leibniz notation. We really like Leibniz. So the power of German engineering. So let's say we have this y function, y equals x squared. Well, if I wanted to take the derivative, one thing we like about Leibniz is it kind of makes them look like they're almost like the top and the bottom are independent from each other, and we can think of them that way. And it's really useful when we get to parametrics. So if I want to find the derivative of y with respect to x, one way to think about this is that we are going to take the derivative of y, which is x squared, over the derivative just with respect to x. So this is just one way to look at it. Well, what would be the derivative of x squared? It would be 2x. Well, what's the derivative of x? It's just 1. So my derivative would be 2x. Likewise, what if I wanted to find the second derivative? Well, what's going on here? We're going to take the derivative of y. But what's our derivative this time? Because the second derivative, my derivative was 2x over, think about this one. This is saying take the derivative of x with respect to x one more time. So now I'm just going to take the derivative of x again. So think about what this says. This is saying I want the second derivative of y. This one says I want the derivative of x, but the second time I want the derivative with respect to x, of just x. And of course here we get 2 over 1, and therefore we get 2. So let's apply this with parametrics now. Now in parametrics, we would say, okay, we're going to cheat. We're going to say let x equal t. Y then would equal t squared. So now let's talk about the derivative. Let's say we want to find dy dx. Now notice we're taking the derivative of y with respect to x, not y with respect to t. If I want to find dy dt, that would just be 2t. Very easy. But we're taking the derivative with respect to x. So I'm going to think of it the same way I did up here. I want the derivative of y. Well, what is y equal to? T squared. The derivative of with respect to x. Well, what's x equal to? It's just t. So the derivative of y with respect to t would be 2t. Whoops, and that was a t there, sorry. And the derivative of t was just 1. So we get 2t. Well, let's take the derivative, the second derivative again. Again, I want the derivative, the second derivative of y. That's what this says. So that's basically the derivative of 2t. But on the bottom, it says I want the derivative of x again. Well, what was x, did we say? It was just t. And we do this, we get 2 over 1. The derivative of 2t is 1. The derivative of t is just 1. The derivative of 2t is 2. There we go. And we get 2 again. Notice we do get the same derivatives, and we should get the same derivatives right there. Now, the reason I tell you this is because we're now going to go over the rule about what's really kind of going on here. But this is a really good way to just look at it. Okay, so let's take a look up top here, and let's go and see if we can find the derivatives. So it says if a curve is smooth, given, and we can write the parametric equations as x of t and y of t, then we can calculate the slope. Well, we know what slope is, right? Slope is the derivative, right? So this is just basically saying that the derivative dy dx is given by this little equation right here. So dy dx is dy dt over dx dt. And that's kind of what we said right over here, down here. We're taking the derivative of y with respect to t and the derivative of x with respect to t. That's kind of what that says right up here. So I like to shortcut it by saying y prime of t over x prime of t. Makes it a little bit easier in terms of just understanding it, provided that the bottom derivative is not 0. This is, now nobody will make this mistake. Everybody will get this correct, the first derivative. It's the second derivative that causes the trouble. So I'm going to kind of go over this, but then I'm going to show you what we did again. To get the second derivative, it's given by this equation. It's the second derivative. It's the derivative of the derivative. That's what this says. It's the derivative of the derivative. So I like to write it this way. dy dx, the second derivative, is the derivative of y prime of t over, now this is the tricky part. That's what this top part right here says. But the bottom part, notice, it's just the derivative of x with respect to t. So it is just x prime of t. And that's how we're going to define this. So notice so what this is really saying is we're taking the derivative of the derivative. We can treat the top and bottom independently from each other because we're finding the second derivative of y. So there's my second derivative of y with respect to t over my change in x with respect to t. And that's kind of what this is saying right over here. So let's take a look at some examples right here. So we want, given the parametric equations, find the first and second derivative. So the first derivative is going to be very easy. dy dx is going to be y prime of t over x prime of t. So y prime of t is not so bad if I take the derivative of y with respect to t here. We're going to get 6t minus 2. So the top is 6t minus 2. The bottom, be careful, this is 2t to the 1/2. Right? If we take the derivative, that's going to become just t to the negative 1/2 because if I drop the 2. So this becomes t to the negative 1/2, or 1 over t to the 1/2. If I don't like complex fractions, so if I invert and multiply, this becomes 6t to the 3/2 minus 2t to the 1/2. And there's my first derivative. Now, the second derivative is a little bit tougher. To get our second derivative, our rule says we're going to take the derivative of y again. So we're going to take the derivative of 6t to the 3/2 minus 2t to the 1/2. And independently, we're going to take the derivative of x again. So x prime of t. So we want the derivative of just x right here. So just over x prime of t. So the top derivative, still pretty easy to do, becomes, what's that? Dropping this down, we get 18 over 2, so we get 9t to the 1/2 minus t to the negative 1/2. Nobody didn't miss that part. But over here, now I can take the derivative of the bottom again. Well, x of t is still 2t to the 1/2. We know its derivative is just going to be the same as up here, 1 over t to the 1/2. And if I invert and multiply, we're going to get 9t minus 1. And there's our second derivative. We'll take a look at some more too. That's really hard to do right there. This is going to be the one question that most of you will probably miss in the first quiz. Be very careful with that, okay? And again, another example later on, we'll take more examples of that, okay? All right. So let's take a look at some examples right here. It says, given the parametric equations 4 cosine of t, y equals 3 sine of t, write the equation, oh my gosh, there it is, the tangent line, where t is 3 pi over 4. So we want the equation of our tangent line. Well, what are the two things that we need? Well, the first thing we need is a point. We can do that by looking at x. So if I want to find x of 3 pi over 4, this is just 4. Well, the cosine of 3 pi over 4 is just negative root 2 over 2. We are in quadrant, right? We're in quadrant 2. Cosine is negative, so it's negative root 2 over 2. And that gives us negative 2 root 2. My y-coordinate at 3 pi over 4, well, that's going to become 3 sine is positive times root 2 over 2, so we get 3 root 2 over 2. So there's our point. Okay, there's our point, our x and y coordinate. Next, we need the slope. Well, the slope comes from the derivative, so that is just dy dx. But remember, this is parametric. Y prime of t over x prime of t. So the derivative of y becomes 3 cosine of t over 4, and the derivative of cosine is negative, so I put negative sine of t. Now you can leave it like this to go negative 3/4 tangent t if you want to. Well, that would be cotangent. Silly me. That would be cotangent of t. There we go. So this becomes negative 3 over 4 times the cotangent, and you're just going to plug in your point, 3 pi over 4, and that becomes negative 3/4, because the cotangent of 3 pi over 4 is going to be negative 1, so it should become positive 3/4 right there. Remember, this is negative 1. So my tangent line, y minus 3√2 over 2 equal to my slope, positive 3 over 4, and then if we get x, it says minus, but we got to put a plus here because the signs change, 2√2. And there is the equation of our tangent line. Alright, go on to video number 2, or the next video, and we're going to take a look at a few more examples. I'll see you then. Bye-bye.